In this video, we continue with our study of normalization to introduce 3NF. We're hunting for 3NF. Our terminology, as we have discussed, is always very important in normalization because we use these terms to define what the level of normalization is. A candidate key is any key, any combination of attributes in a table that can be used as the primary key. Any combination of attributes that uniquely identifies each row in the table. A prime attribute is any attribute that appears in at least one candidate key. And a non-prime attribute is any attribute that appears in does not appear in any candidate keys. Repeating that, a non-prime attribute is any attribute that does not appear in any candidate keys. We can see then that an attribute cannot be prime and non-prime at the same time. Every attribute in the table is either prime or non-prime. A functional dependency is a mathematical formula that defines a relationship between two attributes in the same table. The determinant attribute always gives us the value of the dependent attribute. If I know the determinant attribute, then I can tell you what the dependent attribute is. If I know A, then I know what B is. If I know your social security number, then I know your last name. Third normal form is the next step beyond 2NF, beyond second normal form. To get to third normal form, you must have already gone through and validated second normal form. And that's a mistake a lot of people make in class and on the internet when explaining the normal forms. They gloss over or they completely ignore the fact that you must be in 2NF before you can go to 3NF. Be very careful about that. Always start from 1NF, go through 1NF to 2NF, go through 2NF to 3NF, and then later on we'll see we go through 3NF to BCNF. We are in third normal form if for every functional dependency in a relation meaning table, every non-prime attribute is not transitively dependent on every candidate key. So transitive dependency is a subset of a functional dependency. It's a special kind of functional dependency that uses three attributes or three possibly combinations of attributes. And it looks like that, where the A is a candidate key, B is a non-prime attribute, C is a non-prime attribute, and we can break this down even farther and we can say we have a problem if B determines C. B determining C is a non-prime attribute determining another non-prime attribute, and that's a problem. Now let's peel back the curtain a little bit. We are always going to have this. We're always going to have A determining B because we're in 2NF, and in 2NF every attribute is dependent on all the candidate keys. So sometimes this gets confusing because you're looking for the transitive dependency when really all you have to look for is a non-prime attribute determining another non-prime attribute, and that tells you you are not in 3NF. So use that as your quick and easy way to find 3NF violations. Again, to repeat that, you will always have this because when you're in 2NF, every non-prime attribute is fully functionally dependent on every candidate key. And since A is underlined, we're taking it to be a candidate key. That means B must be dependent on A because we're in 2NF. What we're really worried about then to find out if we have 3NF violations, assuming we're already in 2NF, is that a non-prime attribute is determining another non-prime attribute. If you're building a quick cheat sheet of notes to normalize tables, one of the giveaways then that you're not in 3NF is that a non-prime attribute is determining another non-prime attribute. Here's the fix. This is a formula. This is a set of rules to follow. It always works. Put this in your notes, and when you need to fix a 3NF violation, this is how you do it. You grab that dependent attribute, you remove it from the relation, you put it into a brand new relation, you take a copy of the non-prime attribute that was on the left side of the functional dependency, the determinant attribute, you put that in the new relation. Now you have a new relation with two attributes in it. Step 3, make sure that the non-prime attribute that was the determinant is still in the original relation. So step 3 is really just verifying that you didn't do anything wrong, leaving that attribute in the original relation. And then in the new relation, make that non-prime attribute your candidate key, and you're good to go. Now a subset of 3NF violations are just calculated fields, and we will see those in a moment. In the case of a calculated field, I'm going to have you just remove it from the original relation and not create a new relation. We don't store calculated fields. We'll talk about that in a minute. In this example, we have a relation or table called R. It has 4 attributes, A, B, C, and D. Now we've gotten away from underlining because it gets complicated if there are multiple candidate keys. What you need to be able to do, and this is a skill you have to develop, it's not difficult, is to determine the candidate keys by the definitions of the functional dependencies. You can see in this case, A determines B, A determines C, A determines D. A must be a candidate key because A is a functional dependent. A is a determinant for all the other attributes in that relation. We have a key then, and I will always give you a key. Don't worry, you will always be able to find it. But here's our 3NF violation. A non-prime attribute B determines a non-prime attribute D, and we got a problem. We have to go ahead and decompose this into 2 relations to eliminate that problem. Now what I'm going to do in this example is go through all the steps and talk you through 1NF all the way to 3NF. We know this is in 1NF already, but I want you to ask yourself these questions, and I want you to write these things down if you're given an assignment. So if I ask you to tell me whether or not a relation is in 3NF, I want you to go through telling me that it's in 1, that it's in 2, and then yes or no, it's in 3. So don't skip over the 1 and the 2. I want you to be formal and precise about these things. Is this relation in 1NF? Yes, because according to our rules, there must be a candidate key, and we found that candidate key by looking at the functional dependencies. We found that candidate key to be A, and there are no duplicated columns. There are no subscripts. There's no B sub 1, B sub 2, B sub 3. For example, if we had D1, D2, D3. Now we're in 1NF violation because we have duplicate columns that store the same information. But we don't have that. We have just unique column names, B, C, and D, and we have an attribute A that determines each of those individual column names, so we're good to go. Is it in 2NF? Yes, because every non-key attribute, which we also refer to as a non-prime attribute, is dependent on the prime attribute or all the candidate keys, which is A. B is dependent on A, C is dependent on A, D is dependent on A. So these three again put us in 2NF. Is R in 3NF? No. We've already seen that this B determining D, that functional dependency, is a violation of 3NF. We have a functional dependency where the determinant B is not a candidate key. We have to fix it. Here's the decomposition of R. We're taking the relation R, A, B, C, D, and we're breaking it up into two relations, R1 and R2. You can call them whatever you want. I think R1 and R2 is reasonably descriptive for this general example. We took D out of R1. R1 just contains A, B, and C now. We adjusted the determinants for R1 since there is no D anymore. A determines B, A determines C. There is no D. And we put B and D together into our new relation R2, and we defined a functional dependency B determining D. You can see that B must be a candidate key for that table because B determines all the other attributes. But we're not done. We're not done. You must go back and do the entire process again with each of these tables. I want to see you do that. I want to see you go through the steps and tell me. I want to see you tell me that R1 is in 1NF, that R1 is in 2NF, that R1 is in 3NF. Same for R2. It's not hard to do, but I want to know that you've gone through all the steps from beginning to end so you don't miss anything. And this is from experience because there are so many examples online that don't do this and they just create confusion, that I want you to avoid that confusion and do it the right way. There is an example lifted from Wikipedia, which is never wrong. That's a joke. First of all, before we normalize, what is the update anomaly in this table? Remember, normalization is intended to avoid or prevent anomalies, one of which is an update anomaly. The anomaly is that if you edit, say, the birthday of Al Fredrickson, you have to edit it twice, or 3 times, or 10 times, or 100 times, or 1,000 times, depending on how many rows in the table contain a reference to Al Fredrickson. That's an anomaly. The other things are okay. We plan to update the tournament. We understand we're updating the year. We understand we're updating the winner. But the date of birth is an anomaly. Okay, so looking at the table more closely up here, we see that tournament and year, Wikipedia underlined those two attributes, comprise the candidate key. That is validated down below. Tournament and year determine winner. Tournament and year determine date of birth. We can see then that we have a candidate key, that the candidate key determines all the non-prime attributes, and that looks like 1NF, that looks like 2NF. But are we in 3NF? No, because here we have a non-prime attribute determining a non-prime attribute. That's a problem. In order to fix this, we have to decompose this relation, this table, into 2 and make the adjustments that were detailed in the previous slide. Here's our decomposition. Relation 1, we dropped out the date of birth. We eliminated the functional dependency that referenced date of birth. Relation 2 we created from scratch. It has date of birth. It also has winner, which was the value that determined date of birth. So now we can create a functional dependency in the new relation where winner determines date of birth. And we can give these the once over. Is relation 1 in 1NF? Yes, it is, because it has a candidate key and it has no repeating columns. Is it in 2NF? Yes, because all the columns are dependent on the key. All the non-prime attribute columns are dependent on the key. Is it in 3NF? Yes, because there are no non-prime attributes determining non-prime attributes. Same for relation 2. Is it in 1NF? Yes, because it has a key, winner, and because all the columns are unique, there are no repeated columns. Is it in 2NF? Yes, because all the non-prime attributes are dependent on all the keys. There's only one key winner, there's only one non-prime attribute, date of birth. And that should say winner date of birth right there. Is it in 3NF? Yes, because there are no non-prime attributes determining non-prime attributes. We've determined then that each of these new relations is in 3NF, therefore we have decomposed this table properly. There's a special case which I may give you from time to time, and this is intuitive to those of us that have done any arithmetic. The average earnings up here is the result of a calculation performed using two other attributes. Total amount earned divided by events 1 gives us average earnings. And that's fine for a spreadsheet. That's fine for a report. That is not fine for this relational database that we want to create, because we don't want to store duplicate data. Again, that creates an update anomaly and causes us a lot of problems down the road. It also uses additional storage, which we'd like to avoid. So we are not in 3NF. Now, here is the violating FD that takes us out of 3NF. Events 1 is a non-prime attribute. Total amount earned is a non-prime attribute, and they determine average earnings. So a combination of non-prime attributes determines another non-prime attribute. By definition, this is not in 3NF. We have a problem. We are not going to solve it the way we did in the previous slide. In the case of a calculated field, we're just going to delete it. It goes away. It gets stored in the conceptual design, and it gets carried forward into the calculations of reports and web pages, but we don't store it in the database. So it's calculated on the fly in this kind of database. Now, there are other kinds of databases referred to as data warehouses, where a calculated field is stored and it's supposed to be stored, but not for our purposes. So in this class, what we do is delete the calculated field altogether, and we trust that the developers and the database designer will calculate that field as necessary in a query or a report or a web page. Here's the corrected relation and the functional dependencies. You can see that the average is just gone. Actually, almost gone. There we go. Is it in 1NF? Yes, because it has a key that determines all of the that determines uniquely each row. Sorry, each row is unique by Fisherman. Is it in 2NF? Yes, because every non-prime attribute is dependent on the candidate key. Events 1 is dependent on Fisherman. Total amount earned is dependent on Fisherman. Is it in 3NF? Yes, because no non-prime attribute is determining some other non-prime attribute. Now, if you look at this and you're a Fisher person, you may think, oh, this can't be right. We need to store the boat they floated around in. We need to store the fish they caught. We need to store the date. We need to store whether or not they were an amateur or a professional. Do not overthink these little relations. Just go by the dependencies and the relation definition. We are not intending these to be real-world solutions for problems. We are intending these to be examples of how to normalize. We leave out a lot because we're trying to keep it simple to illustrate normalization concepts. We're not illustrating modeling things in the real world. Here's practice for you. I will tell you that here is a duplicated column. So right away, you know you have a problem because the same information is stored in two columns. So we're not in 1NF. Now, are you going to be able to get from this to 3NF? Yes, you are. But you'll have to start by decomposing this immediately to solve the 1NF problem. Here's another example. Looking at this, you can see there is an attribute called unit that determines county. That attribute unit also determines year, which is great, but there's three columns storing the same thing. Three columns storing some count value for individual years. So right away you've got a duplicate columns problem. You've got to decompose that to solve it into 1NF, and then you can go on into 2NF and 3NF. Actually, this just says go to 2, but since we're on the topic of 3, if you'd like to go to 3, that would be great. Here's another example. Repeated columns again. You've got three columns storing, You've got three columns storing a count of something, some numeric value for three countries. So they're storing the same data three times, different values, but the same kind of data. And then you've got a problem at the end because this is a calculated field, which is the sum of those other three fields. So you've got to decompose to get rid of the 1NF problem. Then you've got what appears to be a calculated field, which is a 3NF problem. But don't get fooled. You have to go through 2NF. Make sure that you go through the 2NF step before you try to solve the 3NF problem, or you will have serious issues down the road. So don't skip 2NF. Don't go directly from 1NF to 3NF because you will get confused. That's the end of this presentation. I encourage you to go back and normalize these by hand on your own. Go through all the steps. Go through this thought process. Is it in 1NF? Explain why. Is it in 2NF? Explain why. Is it in 3NF? Explain why. And if necessary, at each step, fix the problem through decomposition. And then start over again. But because since you decomposed the relation, you've got to start with 1NF again to make sure that relation is correct.